rigid body motion. Specifically, we're working on the kinetics of rigid body motion. And as such, we had to break it into a couple parts. So we're actually going to break this into, well, we're going to break it into 3 parts. The first part we're on, but it's also broken into 3 parts. So the first part that we're working on now is the F equals ma part of the kinetics. Not just what the acceleration, but is how we cause that acceleration. But we also now are including in there this this general business of we're not just strictly accelerating things, but we're also rotating things. This we're also breaking into 3 parts. We did the first part Monday, and that was pure translational motion. However, for the first time really, well, yeah, I guess for the first time really in the work we've done over the last couple of years, the actual size of the object really mattered in the whole part. We did some things with some friction business where we wanted to see if an object would tip over if we pushed it, and then we cared about how big it was. But for the most part, those weren't acceleration problems, those weren't dynamics problems. So that required us to pay attention to the size of the body, and of course that had to do with the moment of inertia of the object. Remember, however, in the pure translational motion there was a bit of a trap, and it came with this particular equation here, or its alternate form, where instead of summing the moments about the center of gravity, sometimes it made more sense to sum the moments about some other point, just as it had in statics all those times. Sometimes problems get a little bit easier if you pick a different moment about which to make your sums. Sometimes the forces disappear from the equation, so the solution's just easier. If you do that, don't forget that these subscripts, you can use any form of this equation as long as these subscripts match each other. And that's where students sometimes get into some trouble. Because for translational motion, naturally there's no angular acceleration. If there was, then we'd have a rotational component, and we don't when we're talking about pure translation. In that case, then, this alpha equals 0, but this one does not, because remember that we had to add on to it. This is actually an angular momentum term. And now this alpha here equals 0. This term left over does not equal 0, which shows that this alpha is not equal 0. As much as you may be tempted to make it 0, it's not. It's a very easy trap to fall into, which is my subtle way of saying I've fallen into it. So I've found over the years it's just best to really make a belabored point of being careful with this. Today we're going to look at pure rotation as part of the problems. And in this case now, there will be some angular acceleration. And this doesn't become as much of a problem because alpha isn't 0 in any of the parts of it, so you're not going to get trapped with the difference between these two things. If we need to sum moments about a different place, we'll just do it. It is still true that this part must be in here if we're not summing about the center of gravity, but we'll just add it in, and we'll do a couple problems with that, and it'll make, hopefully it'll make some good sense. And then Monday, we're going to put these two back together to get the general motion of rigid bodies. General motion being both translation and rotation at the same time. again, the simplest example of just that type of motion is a car tire. As the car moves along, the tire rotates and translates. Then we've got to put those two motions together to get a good feel of what we're doing. All right. Before we go any further, I want to make sure that you know how to get this moment of inertia when needed. So there's 5 ways in this class to get the moment of inertia. Now, remember, if you need the moment of inertia about another point, you use the parallel axis theorem. But 5 ways to get the moment of inertia for these problems. Not in any particular order. They are, 1, it might just simply be given. You'll notice in some of the problems when you need moment of inertia, it just simply says so right on there what the moment of inertia is. Pay attention to the moment of inertia about which point or axis. 2, you might need to look it up. If we're working with a regular shaped body, then it's just in the tables, and you've seen those before. We have 2D tables. Those are tables, I think it's 3D, and 3-dimensional tables, 3-dimensional objects is table 4D. So if it's just an ordinary regular shape, go there for the moment of inertia, particular simple shapes. If it's neither one of those, you might need to calculate it. And that can take 2 forms. One, you might need to integrate it directly, right from the definition of the moment of inertia. Integral of r squared dm. That will work for semi-regular solids because you're going to need the functional relationship between the shapes to do the integration. But as we established in the earlier class this morning, we still love integration as much as anything we ever do. So that's a possibility. It's also a possibility, though, remember, to take various regular shapes from the tables and combine them into a compound shape to get the moment of inertia you might need. The 4th way, again, this is no particular order, it's just maybe the thought, the steps you go through until you find it. You can also get it from the definition of the radius of gyration, which is we use the little letter K. It also is about a specific axis, so again, these 2 subscripts must match each other. You can have the radius of gyration about a different axis, just as you can have the moment of inertia about a different axis. This is an artificial construct. It's as if we've taken whatever object we're talking about, and we know whatever its moment of inertia is. We move all of the mass out to some distance from the center of rotation, k, the radius of gyration, and it's as if we put all of the mass right there. So if we've got some wheel of some kind and it's got a rim on it that might be thicker than the inner part, or even could be a spoked wheel of some kind, whatever its moment of inertia is, we can get an idea and a relationship between that and the radius of gyration if we imagine an artificial object with all of the mass located at this distance, the radius of gyration. Those 2 things, if they have the same moment of inertia, then the radius of gyration is the place where all the mass would be concentrated in an artificially infinitesimally thin ring at that distance. It's just another way of representing what the moment of inertia is. And then the fifth way. Anybody know what that one might be? But no, that's not on there. Asking me is not on there. Actually, it might be worth it on tests. It's really easy to type up a test and forget to put something in. I never do that, but I've heard other professors do. There are problems where you just don't need it. You might think you do, but as you work farther through the problem, you'll find out that it later cancels. If you remember, we had some problems over the years where we needed the mass, but the mass ends up canceling and we don't need it in the end anyway. So there might be some problems where you think you need it, but you don't. And you might not need that, and you might not know that until you get a little farther. So if you're doing a problem and you don't have the moment of inertia and you think you need it, take the problem a little bit farther and it may just simply cancel out and you're fine without it. And then you don't have to bother me. Which at this time of year, you do at your own peril. And that is on tape. All right, so we're ready to look at a couple rotational problems. All right, the general setup of what we're doing I can illustrate with just a simple picture. We've got something that can rotate, in this case what's called a physical pendulum. It'll have some place where its center of gravity exists, and it may have some angular acceleration and it may have some angular velocity. I'll just arbitrarily choose them in that direction, mostly because when we do so, that establishes our tangential and normal directions if we so choose to use those. The tangential direction is always in the direction of the motion at the moment, as shown by the omega in that direction. And then the normal direction of motion, normal coordinate direction, is always towards the center of rotation. So that just simply sets up our general methods. Some of the problems, those coordinate directions happen to fall in the typical horizontal, vertical directions we're used to so often, and so you can just go ahead and use IJK there if you want. But we've got a couple things that we can use for our typical two-dimensional problems, as this one is. We know that if the forces are unbalanced on it in any way, then the center of gravity will accelerate. So for our purposes, that's two equations, because that's in the x and the y direction that we could do that. And then we can sum the moments about some point, and it may be the point G, it might not be. And for our two-dimensional problems, then that's one equation. If we're doing three-dimensional problems, then there are 6 of these available to us. Oops. I need the M in there. That makes more sense. There we go. And these are our kinetics equations of rigid body motion. And then, of course, we've got any possibility, any available kinematics equations that we can bring in. as needed. For example, the acceleration of the center of gravity will be relative to the acceleration of point A, if point A is the pivot, plus the acceleration of G relative to A. But of course, in pure rotational motion, like we're looking at today, that pivot point doesn't accelerate. It will when we look at general motion on Monday, but today it doesn't. We're looking at just pure rotation, so the center of rotation itself does not accelerate. So we can count that as, well, let's see, we can do more with it. Remember then that that is R alpha in the tangential direction plus R omega squared in the normal direction. And typically for us well, depending on the problem, that could count as either one or two equations. And then the other kinematic piece we can bring in has to do with the velocity, which is also dependent upon the velocity of point A and the velocity of G relative to A, just as we looked at the week before. But in pure rotational motion, point A is not moving. So we've got then just the piece R omega in the tangential direction. Because there is no normal component to the velocity of G. G cannot move anywhere closer to point A or farther away from point A because it's a rigid body. So there's two more equations there in the kinematics that we can bring in, and any others that might be appropriate, but that pretty much covers it all for the ones we want to use. So that's the general setup of where we're going today. We'll do a problem now to help illustrate it. So imagine we've got a slender rigid bar. At that instant, it happens to have already some angular velocity to it. It's 3 meters long and has a mass of 20 kilograms. And just at that instant, as it's rotating past the horizontal, a moment is applied about this point. Maybe we'll call it A, certainly rather than G, because G is at the center. The type of thing you do, if this is some kind of hatch coming down and you need to apply a braking moment, you'd apply one in the opposite direction, and it might not occur until some particular point in the motion. This one we happen to have it as an aiding moment, but could be virtually anything as we go through this. So we'll give that a magnitude of 60 Newton meters, and omega 0, we'll say at that instant, is 5 radians per second. And so we want to find two things in particular. One, once it passes that point and once it has the moment applied, what's the acceleration now? And what's the reaction at A? We'll find that it's a little bit different than we might have thought if we'd approached this with the naivete we would have had doing it in statics. Okay. Two things we generally need to do. Generally, to find forces, we need a free body diagram, and to find something about the particular motion, we'll need a kinetic diagram. You're welcome, if you're careful enough, to do these on the same diagram, but just be careful with it. If you're drawing acceleration vectors on a free body diagram, make sure that they don't look like force vectors, and you go ahead and put them into the particular solution. So, free body diagram. Of course, we have a bar that has some particular weight to it. We don't take that as an unknown since we know what the mass is. There's also some reaction at A, so we'll break that into components. Let's establish a coordinate system. We'll just use normal and tangential coordinates. Tangential down, because that's the way it happens to be moving at the time. That will give us a positive on some of the velocities and the accelerations we need them. And the normal is always towards the center of rotation. So that'll be A in the tangential direction. And then A in the normal direction as well. Is that it? Now on the free body diagram, we also have to draw any applied moments. So we have this applied moment MA as well. Anything that's, any of the kinetics that's affecting the kinematics of the object goes on the free body diagram. All right, then the kinetic diagram, we'll put what we expect to be the result of any of these forces and moments as applied. So naturally, we expect that the center of gravity will accelerate, and certainly at that point we expect it to accelerate. Well, that's our tangential direction, so let's just leave it as that. We will sum the forces and the moments to determine what makes up that bit. We also expect some angular acceleration, of course, but we're trying to find that. Not only is it falling past that point, and would probably be accelerating in some way anyway, and I believe that was a Physics 1 problem that we did. It also has this moment applied to it at this instant that will contribute to the acceleration. What else? There's one other piece, and this is the piece that's easier of any of them to forget, and is also the piece that will show us that this normal component on the reaction is not zero. Certainly our temptation would be to say, oh, this has got to be zero, but it's not. These are not statics problems. David?
Centripetal acceleration.
The centripetal acceleration. And we'll put that as acceleration of the center of gravity in the normal direction. And that's always defined as straight towards the center. So the part that what we've drawn in the free body diagram causes what we expect to see in the kinetic diagram itself. And so we do what we've always done when we're looking for accelerations and reactions and the like. We sum the forces and the moments. So sum the forces in the normal direction, I guess, will tell us what that normal acceleration is. And then we'll do the same thing in the tangential direction, and we'll do the same thing with the moments. So this part, this is, well, we've done this kind of thing before. So let's see, A-N, that's in the positive direction of how we've established, well, because the normal coordinate is always towards the center of rotation. AT, of course, doesn't figure. MA isn't a force anyway. And so that's all there is. But, again, that's not equal to 0 because that's the centripetal, that's a result of the centripetal acceleration. And that we know to be, just like it always is, R omega squared. And so I think we've got all those pieces. So we can actually calculate this one. Mass of the object's 20 kilograms. What do we mean by R? Is that the whole length of the bar? Or this distance out to the center? You said something, John? Yes, it's the distance from the center of rotation to the center of gravity. Because it's the center of gravity that we're talking about right here as the acceleration. So that's how we have to peg it. So that R will be 1.5 meters, and omega at that instant, remember, it has an angular velocity of 5 radians per second. So that will give us, let's see, kilogram meters per second squared. Remember when we use the kinematics and the kinetics, the radians disappears as a unit. So the units work out, and that comes out to be 750. I think. Is that right? 750 newtons. So that one was easy. Just kind of a warm up. You know, get the juices flowing here now. So try the tangential direction. Sum the forces. If they don't balance, and we certainly wouldn't expect them to, we'll have some tangential acceleration. So let's see, positive is down, that's the tangential direction, so it's W minus AT. Those are the two vertical forces. Remember, the moment's not a force, so it doesn't contribute to this. And that's going to cause the center of gravity to have some tangential acceleration. But that tangential acceleration is going to be R alpha. We have M and R, but we don't have alpha. In fact, that's one of the things we're supposed to find. So there's the first appearance of our unknown. So we've got to keep going. We have two unknowns, alpha and AT are in here. We need to figure out more. So we'll sum the moments about the center of gravity. And that should give us some idea of what the angular acceleration is. Well, something about the center of gravity, because for a slender rod, that's easy to find. It's one of those ones that's in the book. IG equals 1/12 ml squared. And we have all those. We know the mass is 20 kilograms. And we know the length is 3 meters, so we can figure that out. As requested this morning, you want me to do the hard stuff, so you don't have to. So this is 15 kilogram meters squared. All right, so let's set up. We'll take we expect the acceleration to be clockwise, so we'll take that as our positive direction. Doesn't hurt to indicate that, just so you don't mess up. So sum the moments about G. MA is a moment on the entire piece, so it goes in there just like that. That's all we need to do with it. AN goes through G, so it has no moment that it contributes. AT has a positive direction to it, which would be, its moment would be ATR. And W goes right through G, so we don't put it in there either. So that's good. We haven't introduced any more unknowns. I think we only have two unknowns anyway, so we're coming up on the two equations we need to solve it. And that's going to equal IG alpha, and we know what I is, and we're just looking to find alpha. So there we go. There's two equations, two unknowns. Two unknowns, alpha and AT, and our two equations, the two equations we just came up with. So as you go through these, be careful. What we're doing here in dynamics is different than what we are doing in statics. Don't try to apply your statics equations unless you know for sure that in a particular direction there's no acceleration. It would be very, very tempting to have at this point said AN equals 0. But it doesn't. As we saw, it's not only not 0, it's worth 750 apples. All right, two equations, two unknowns, then we can solve it. It's just algebra left, so I won't belabor that. We get alpha of 5.9 radians per second squared, and we only need the tangential component of the reaction force because we already have the normal component, and this is 19 newtons. So in this particular situation, it's that normal component that you might have thought was 0 that is significantly larger than is the tangential component. That, at least to me, was not at all intuitive. So you've got to trust the equations. You've got to be careful with them. You've got to avoid the temptation to just start knocking some stuff off as 0 because you think it should be. It will make the problem easier. As calling a bunch of stuff that's not 0, 0 always makes the problem easier. It just also makes the problem wrong. So be careful with it. All right. Questions on that before I clean up? Pretty straightforward. Just be careful. Take your time through it. Make sure you get your minus signs right. Make sure you don't miss any of the parts. But that's always been the case. certainly ever since you started with me in Physics 1. We've been watching minus signs and making sure we're doing complete problems. So any questions before I clean up? And we do an alternate solution to this? Okay, alternate solution. Well, there's no easier way to have found that AN, so we're not going to find an alternate solution to that. That only appeared in one equation, and so there's only going to be one way to solve for it, and that's summing the forces in the normal direction that we already did. But we have an alternate possibility, so alternate solution. Let's sum the moments, not about G, but about A. We have two forces that go through A. One of them is unknown, so let's sum the moments about A and see if that isn't a little bit easier. Remember, though, that we need the moment of inertia about A. But for a slender rod, that's no big deal. That's one of the ones in the book. You might even remember that for a slender rod, it's just 4 times what it was about its center of gravity. That's only true for a slender rod. It's not true for other pieces. It's just true for this, for a slender rod. And by slender rod, we mean that the diameter is much, much less than the length, so we're not even concerned with the diameter. Okay, so let's give this baby a try. Let's see. MA is still there. That's just one of the givens. That's part of the kinetics driving the whole problem. And W causes a moment in the same direction. Its moment arm is R. They happen to be perfectly perpendicular at the moment, so that's easy. And that's all there is. The other two forces go through the point A. So it's then IA alpha. And the only unknown in that problem is alpha. And so it is a little bit easier to solve for. And much to our relief, you get the same thing as you did before. Still, though, you need to solve for the other component of the force, so you have to then sum the forces in the tangential direction and actually get the tangential component then of the force there. So it doesn't cut down on the number of equations, but it does mean that each of the equations independently solves for one of the unknowns, and you don't have to use a system of equations. So it's a little bit easier in that regard. Questions there, because we need an alternate solution. Just when you were hoping things were easier to decide about, they aren't necessarily. So we'll have an alternate solution. Still, AN can't do anything with that, but what we can do is just look at the summation a little bit differently. It could be that we didn't have something as simple as a slender rod to use, and thus maybe it would be a pain to find the moment of inertia about a different point. So we can go back and do it about the original point, the center of gravity, but we need to take into account the fact that that's not the point where we're summing the moments themselves. So you have to put it together like that. And taking the clockwise direction as positive as before, because that's where our alpha goes. That looks like MA plus WR, just like before, because we're still summing the moments about A, just as we did before. It's just now things are a little bit different because we use IG instead of IA. And then the mass is the mass of the bar. AG, with respect to point A, is R alpha. So we only have one unknown in this equation, but it does appear twice. And then D is the distance between the 2 points, which for us is that R. So that's AG, specifically AG in the tangential direction. And then R is just that part D. So the numbers come out to be exactly the same as they were before. I have a question for you. This AG, I've got AGT taken care of. How do we handle AGN? Because that is not 0. That took care of AGT, not AGN. I'm going to let you think about it a little bit, because I need to go get a new piece of chalk. I'm working way harder than I expected. John, you okay? It's my chalk sponsor.
Chalk dust coming off the board.
Oh, come on. I don't generate chalk dust, do I? Little product placement there for a couple $1,000,000. All right. What'd you decide? How do we handle the normal component here? Because this is not specific to either direction. This is just the moments about A, and the kinematics they cause. Who's got an idea? For $1,000,000? What?
P squared over R?
Well, we could certainly do. We can find that. It's it's R omega squared. We have both of those, so I could certainly put it in. In fact, just for the sake of argument, I will. So there's R omega squared. That is AG in the normal direction. David?
I was thinking it didn't count because it was parallel to D.
No.
Okay.
You're close, but you need to be even more specific than that. What is D for this component? It's not R. It's 0, because this component goes straight through the point A, and it's the minimum distance between that acceleration and the point of interest that is d. So it has a d on it, but for that component of the acceleration, it's 0. So I told you this was going to be advanced physics 1. Some of these things are pretty subtle. You need to trust the physics, trust the equations, and be careful about jumping to conclusions just because some things might fit. They don't necessarily. So, one equation, one unknown, alpha. It just happens in 2 places, so it's a little bit more complex. It also has this potential trap in it, but that's why it's the second alternate solution and not the first alternate solution. But you get the same answer. Get a little shell shocked from dynamics here? Yeah?
That's 2 pages left, so I don't know.
Oh, let's see how we're doing. It just gets harder and harder. No, we can do it in 2 pages, I promise. If need be, I'll buy a sheet of paper. Okay. Another problem. Harken back a little bit to Physics 1 for you, those of you that had it. Not those of you who have had it with me. Those of you who have had it with me. All right. Imagine a pulley center is mounted somewhere to, hanging from a sky hook or something. And we have a mass on it. All right. Starting from rest, find the angular acceleration of the pulley. All right. Some of the details. The radius of the pulley, 0.4 meters. The mass of the pulley, m sub p, we'll call it, 60 kilograms. And the radius of gyration. What this really tells you when we have that instead of the moment of inertia is that it's not a uniform, might not be a uniform density solid. Certainly it has mass distributed in different places, maybe more at the rim or something. Maybe there's some spokes or something that helps it turn on the axle, whatever it is. Doesn't matter because that leads to it directly to the moment of inertia if that's what we need. And that is, it's a regular length. It's the radius at which we could concentrate all the mass and still have the same moment of inertia. And then the little mass there itself, call it the mass of the block, is 20 kilograms. All right, so find the angular acceleration of the pulley. So I'll leave that to you a bit. See what you can put together. Start with a free body diagram and separately if you wish, or you can combine them, a kinetic diagram as your preference. Look at Travis, he has no, he'll draw circles and just keep going. There's no stopping Travis. Do not get between Travis and the solution. Alright, so set up your free body diagram. Do not assume forces are zero, because we just showed a problem where it might have been very tempting to say certain forces were zero and they're not. And remember, every force is caused by something real. There are no forces caused by the motion. The motion causes the forces. But just like you can have too many, you can also have too few. So get just the right number of equations, forces in the free body diagram, and then proceed. Give you a couple minutes on the free body diagrams. Most of you are getting them. Some of you are throwing in a couple extra just for fun. You ask John what he's doing? John's throwing arrows in all over the place. Most everybody's got the basis here for a free body diagram. Of course, the pulley weighs something, so there's some force down. It's countered by reaction. We'll call it AY. That thing's not going anywhere, so we might as well use XY coordinates. And then AX, I happen to pick in this direction. And, of course, the tension in the line. That's actually what's causing it to turn. That's the applied torque as far as the drum is concerned. And then we've got the mass with the same tension up and its own weight down. I think I call that B. So there's WP for the pulley and WB for the block. So that should be your free body diagram. Any major disputes? The kinetic diagram is the cause of those forces. It's going to cause the wheel, the pulley, to rotate. It's not going to cause the pulley to do anything else. That's all it's going to do, is it's going to start to rotate. It's going to acquire some angular acceleration, nothing else. The block will have some translational acceleration, and of course those two are related. R alpha, where R is the radius of the pulley, is going to be the acceleration of the block. How can I say that? That's a bit of an assumption, but I talked about it the other day. Remember what I called that? Term. That is only true if the rope is not slipping on the pulley. If that's slipping on the pulley, if the rope is slipping on the pulley, not wrapped around well enough, then I can't say that. That's equivalent to saying that this point on the edge of the rim will have the same acceleration as the block at that instant. That point also has a normal component because it's in a circular path, but that has nothing to do with the block. The block is not going to have a normal component to the acceleration because that point will go in, but the contact point with the rope will not. It will stay where it is. So now we've got enough of the pieces, and you can now start to solve the problem. So we've got 1, 2, 3, looks like 4 unknowns. However, 2 of them, the 2 reaction forces, go away if we sum the moments about the center point. We're not asked for those, so that'd be a good place to start. Plus the radius of gyration that we have is about the center. So I don't know if it's worth calling that A or calling it G. It doesn't matter. It's just semantics. I don't like it that way, not when they don't match. So, point A and the center of gravity are the same. Okay, pick the positive direction as the direction we expect a positive acceleration. Just makes things a little bit easier, less hassle with minus signs. So the moments about point G or A, the center, is just the tension at a particular radius. And that is positive in the direction specified. And that'll equal kg squared mp alpha. So 2 unknowns. One equation, so we're not ready to solve yet. We've got to do something else. What? It'd be nice if the 2 equations didn't bring in any more unknowns into it. If we can do an equation without ax and ay, we'll be that much closer to solution. If we bring in an equation that has a and xy, we've got to keep going because we've got an unknown. Right now we have 2 unknowns. If we can keep it at that, one more equation will do it. Well, we sum the forces in the vertical direction. That brings AY into it.
Just use the one you have right
What?
there. R alpha is equal to AB, where AB is the mass of the block times acceleration of gravity.
Well, if
Or not
we
gravity.
sum the forces on the block, it'll give us that acceleration, but that acceleration we know to be directly related to alpha. So technically we would bring in another unknown, but it's very easily taken out with perhaps our simplest equations. So sum the forces in the y direction on the block will cause the block to accelerate. And we've got T up, WB down. That will cause the block to have an acceleration that we know to be related to R alpha. So there's a second equation with just as many unknowns as before. So it's a matter of high school algebra to solve that, and you'll have to do that because I didn't write it down. Oh wait, there it is, 11.3 for the angular acceleration. We should guess ahead of time and have kind of an office pool on what these numbers should be. Just allow somebody to make a little bit of cash before we head out for summer vacation. All right. There's another way we could have solved this one. And it eliminates an unknown by taking the block and the pulley as a single system. And not separating them like we did here. We didn't need to find T, so it may not have been the most prudent thing to do to bring it into the problem. Still, we need a free body diagram. So we've got the weight of the pulley there, the weight of the block there, and the two reaction forces, neither of which we were asked for, and we didn't bother finding them the first time. Since we don't want those, it makes sense again to sum the moments about that point. Where this is of the entire system, we can make it a little bit simpler. If we use IG. Remember, point G and point A are the same anyway. But we need to add on the effect of the acceleration of the block itself. We don't know the moment of inertia of that whole system with respect to point A because the block itself changes that. But we can split that out as a separate part then. And now we don't need to know the tension, nor do we need to know the reaction forces. So it comes out to be very similar to what it was before. None of those have anything to do with it. We have WB at a distance r is the only moment applied about point A. And then this is kg squared m alpha, mp alpha. I had that over there, didn't I? Yeah. That's just the moment of inertia from the radius of gyration. And this is, by the way, that's the block, and it's the point of it being off center. So that's MB, R, alpha, where this is the radius of the pulley. That again is our no slip condition. And then D is the radius of the pulley yet again. So that little piece is the acceleration of the block. And this little piece is D, the distance of the, actually the line of action of that acceleration with respect to the point picked, which was point A. Again, it's a trade-off. There's only one unknown in there, just the alpha. Everything else is given. However, getting to that point is a lot more subtle than I think this was. I think that's a lot more straightforward. So maybe it's an academic exercise for you, which one you want to do. But it's your choice. Even if you're not going to use something, I think it's helpful to see how it worked, even without using it. So, oh, I think we need a get out of class question. Head into the weekend. What?
Let's get
Yeah, but then I gotta ad lib for 12 minutes, and that's not pretty. We've all seen the kind of things I say when I'm winging it. Okay, so here's a problem for you. It was actually a quiz problem from a couple years ago. Pulling a crate up a ramp using a winch. And the details are the ramp is 20 degrees. The coefficient of kinetic friction between the block and the slope is 0.4. The block is 45 kilograms. And the winch is a radius of 15 centimeters, a moment of inertia about the pulley part, 4 kilogram meters per second. Per meter squared, kilogram meter squared. And the moment applied by the motor to the pulley is 50 Newton meters. So that's the motor turning the pulley itself. So not only does the motor have to haul up the mass, it also has to get the pulley itself started. Find the, well, just set up the equations. Finding the acceleration or something is just a matter of solving the system of equations. That's just algebra. So let's get the physics set up. Set up the equations however you choose. And then it's just a matter of, if you got the equations right, then it's just algebra after that. And that's not what we're here for. So, free body diagram. The kinetic diagram is pretty simple in some of these problems. It might not be worth it. It could be worth it in more complex problems. Might be worth it, not worth it in these. Especially as small as some of you draw. Yeah, some of you draw. Okay, so set up the free body diagram, set up the equations. You will need all three forces in the x direction and y. Probably makes sense to incline them with the slope. If we're looking for the acceleration of the crate, if you incline your axes with the unknown, it usually just makes the solution a little bit simpler. But you can do anything you want with it. So, free body diagram of the crate. Now, some of that is statics. The dynamics is just the T, a little bit of W down, and the F down. But when you sum the forces in the different directions, it comes out in the wash anyway. That's how we get the normal force that we need for the friction. And then for the winch, we've got the tension. We've got reactions and its weight, but the weight wasn't given and the reactions weren't asked for, so all we're really concerned with is the dynamics of the situation, which is just the tension that's causing some angular acceleration. Oh, it's got the moment on it too, of course. But all that's going to result is that alpha. So we can wrap everything up with some of the forces in the XY direction on the block and some of the moments on the winch. Should be able to relate all those. Acceleration of the box or the crate or the whatever, coffin. No, not 45 kilograms. They listen to a murder mystery. Who killed patient Stanhope? I'm going to find out until later. Yeah. You know, I live 1 mile north of here, so it's a long drive.
Fully on mass?
Nope. Well, yeah, it does, but not given. Huh?
Why do you have a downward force on the pulley?
Because it exists. But those are static forces. This is the dynamic force that causes the acceleration. So we don't need the mass on the pulley. The mass of the pulley. If you sum the moments about the center of gravity of the pulley, those don't come into it because they go right through there. So they're not a concern. If we sum the moments about G on the pulley, all that's in there is T and M. And M is given. T we don't have, but that's what's going to cause the acceleration of the block up the table, so we'll be able to find that. What we're seeking is the acceleration of the block. So just set up the three equations, and then we'll see what we got, see if we all compare. On the block, if we sum the forces in the x direction, that's what's going to cause the acceleration we're looking for. That'll have in it the friction force. We need the normal force before we can solve for the friction force. So we'll also have to sum the forces in the y direction. But it is in a static balance in the y direction. So a dynamic balance in the x direction, but not in the y direction. So that'll give us n, which will give us f. So we'll have two unknowns, the tension in the line and the acceleration in the block. And then the tension in the line we can solve with the third equation. Sum the moments about g for the pulley. That way we don't care what the weight of the pulley is. We don't care what the reaction forces are that supporting the pulley on the motor. That will leave us with three unknowns. From this one, we're going to have T up, F down, which is mu n, minus W sine 20. Is that right? And that's all the x components, and so that's going to cause the block to accelerate in the x direction. We're looking for that. So that should be the equation, and then we also need, of course, that F equals mu k n, which we find from the y direction. So that's mu k w cosine 20. The sum of the forces in the y direction is solely going to find the normal force for us that we need for the friction. So how are we doing? T is unknown. F we'll take as known because it's just a matter of filling all those little pieces in. And the acceleration of the block is unknown. So some of the moments about the center of the pulley, taking the positive direction to be the direction of the acceleration. Just, you don't have to, but it makes things a little easier. So we've got the tension trying to turn it one way, the moment exerted by the motor trying to turn it the other way, and the difference between those two is going to cause, actually I drew the acceleration in the wrong direction, so it doesn't matter, it would come out now as a minus sign, so we knew we drew it in the wrong direction. So now how many unknowns? The tension, the acceleration, the tension's already there, R's given, M's given, alpha's not given. Three unknowns, two equations. This doesn't count as the second equation because we use that just to find n. So essentially two equations, three unknowns. Not treating the friction force as an unknown, just because it's a matter of filling stuff in. What's the third equation? Come on, we're 45 seconds into your weekend. Third equation. Who's going to rescue the class and send us all home? Travis?
Acceleration in the x direction is r alpha.
the no slip condition, assuming the cable's not slipping on the pulley. And there's your last equation, and now it's just a matter of the algebra to solve it. So there we go. We'll do general motion on Monday.
If you have an